Okay, continuing on to the final lesson of this unit, geometric series, right? So we have arithmetic and geometric, right? Remember, a sequence is an ordered list of numbers, right? A series is when you add up those numbers. So arithmetic is when they had a common difference, so we're adding or subtracting. Geometric is when there is a common ratio, which generally means we're multiplying or dividing. But when we're dividing, we write it as multiplication. So don't forget, if you're dividing something by, say, 3, that's the same thing as multiplying by 1/3. So we can rewrite all the division as multiplication. So think about it that way. Okay, and don't forget, I wrote over here recall because we need this formula sometimes. We need the general term of a geometric sequence, okay, which is Tn, the term, is a, the first term, times r, the common ratio, to the power of the number of terms minus 1. All right, so now let's talk about the formula that's used for partial sums of geometric series. So remember, why do we say a partial sum? Because it can go on forever. So we just say, well, how many numbers in that do you want to add up? The first 10, the first 20, first a million, whatever, right? N is still the term number, A is still the first term, and R means what it meant before, which was the common ratio. Now remember, how can we find that? Take any term and divide it by the previous term. That's how you can find R. All right, so let's do this first one. Nice, simple one to start, right? Determine the sum of the first 20 terms for this series. All right, so A is the first term. Well, that's 1. There you go. So T1, right? That's what A is. All right, what is R? Well, take any term divided by the previous. So 2 divided by 1, or 4 divided by 2, or 8 divided by 4. You always get 2, right? All right, and they want us to make n 20. So this one's going to be pretty easy. Just punch it in the formula. I'm sure you could do it without any of my help, right? So we're going to replace n with 20. A, right, is going to be 1, so nothing special there, times 2 to the power of 20 minus 1 divided by 2 minus 1. Now, we got to be careful here, right? So, what did I write? 2 minus 1. Where's the minus sign? There it is, right? R minus 1. All right, so in this case, obviously, this is 1. 2 minus 1 is 1, so the 1's just cancel out. So all we're going to end up having is 2 to the power of 20 minus 1. So punch in your calculator, what's 2 to the power of 20, right? Which is going to be 1,048,576. Subtract 1, and there you go. That's how much you get if you add up the first, oh, those pesky 4s, eh? If you add up the first 20 terms of this geometric series. Now remember, geometric, we're multiplying here, so these numbers grow really quick. So don't be surprised if you get some really big numbers or some really tiny numbers if we're looking at them shrinking, okay? Let's look at example 2, where instead of growth, we got decay. It's going to be shrinking. Okay, so now we've got one where the numbers are getting smaller. So A is 75. Now, what is R? Now, you can tell, you should be able to just figure out that, look, what am I doing each time? What am I multiplying this by? Well, how did I go from 75 to 75 over 2? I multiplied it by a half, right? Now again, if you're having trouble, take any term and divide it by the previous term. So for example, what's 75 over 2 divided by 75, right? Take term 2 and divide it by term 1, right? Well, we're going to have 75 over 2 times 1 over 75. Obviously, the 75s cancel out, and we got 1/2. So I'm timesing by a half each time. And they want to do the first 20 terms, so n is going to be 20. So let's punch all this stuff into our formula. Let's be really careful, see what we can come up here. Sum of the first 20 terms. The formula above was, let me just write it out for you again so you can see what it is, right? A times r to the power of n minus 1 divided by r minus 1. So 75 is A, r is a half, so let's be careful. Now you can put that in. In this case, we can make it a decimal if you prefer, because we're just going to get a tiny decimal number, you'll see. So let's make it 0.5 just to keep it simple here. To the power of 20 minus 1 divided by 0.5 minus 1. So that's going to give us negative 0.5. So when I do this, I'm going to spare you watching me bore you by entering all these numbers in the calculator. When I do 0.5 to the power of 20 and I minus 1, I get negative 0.9999. Keeps going, right? All right. And on the bottom, we have negative 0.5. So I'm going to take that number in my calculator, times it by 75, and divide it by negative 0.5, and I get 149.998 ... Okay, there you go, right? So it's close to 150, but it's not 150, right? Now I want to point something out to you here. What if we did the sum? So I have a kind of little thinking question here. What if I did the sum, instead of the first 20 terms, what if I did the sum of the first 100 terms? Well, you can watch me punch this on my calculator. All I would do is change the 75 here to 100, okay? So the same thing, so I won't bore you with the steps. I'll let you, I'm sure you can handle the calculator part, right? So I'd go 0.5 to the power of 20, subtract 1, I'd still get this number here, and then I'd times that by 100, right? Instead of, oops, I'm sorry, I'm thinking of the wrong spot. Not the 75 changes. Oh man, goofy me. The n changes, right? My bad, which is this number. My bad, that's the only number that changes. Sorry, space out. All right, so if I change that number to 100, right? So what if I made that 100? 0.5 to the power of 100 minus 1 times 75, right? Divided by negative 0.5. Guess what I get? I get 149.999. It's got a whole bunch more nines, yada, yada. What if I did to 1,000? Guess what I'd get? 149.999. Now, it's not the exact same number. The decimal far, far at the end is going to be different. Same thing if I did it to, a humongous number. I could keep doing this. It's still going to be 149.9999999. Now, somewhere way back there, the decimal will be different. But notice how it never reaches 150. Why is that, right? These numbers continually shrink, right? They get smaller and smaller and smaller. There's a name for this. It's called Zeno's paradox. And there's a lot you can read about it. But the idea is we're getting smaller and smaller and smaller. We're never going to get a number that's big enough to get over the hump and turn to 150. It'll never happen, right? They just get tinier and tinier. You're just adding smaller and smaller decimals, right? Because as this pattern keeps going, these numbers keep getting smaller up here, right? You get tinier and tinier. So you could do this s to the billion, to the trillion, right? It doesn't matter. It's still going to be that same thing. So this essentially has a limit. And we're going to learn a lot about limits in grade 11, right? Or grade 12, okay? If we graph this thing, okay, on a graph, do you remember it has what we call an asymptote, okay? So it gets closer and closer and closer to this number, but it never touches it. So if we did a graph, this is going to be not a very accurate graph. I'm just going to do like a super rough sketch here, right? Here's my graph. The idea is at 150, there's a horizontal line, right? And these numbers, as we keep adding them up, as they get closer and closer, it just gets closer and closer and closer and closer. It would actually be starting at like here somewhere. Sorry, my bad. Right? But it would get closer and closer and closer and closer, but it would never ever touch 150. So if this is 150, right, they're never going to make it. They're never going to cross that line. They're just going to infinitely get closer to that line. So that's something to think about. I wanted to point that out to you, okay? All right, one final example here. Okay, the final example is going to be one where we need a system of equations again. Well, how do I know that? Okay, they're telling me the sixth term, right? So they're saying, all right, T6 is 224, all right, and T17 is 458,752. So this is like giving me 2 points, right? Like it's like giving me 6, 224, 2 points on a graph, right? And 17 over, right? It's 2 points. So we have 2 points, but we don't know the A, the starting amount, and we don't know R, the common difference. Now, you could fiddle around, but what you need to be able to do and show me is that you can set up a system of equations. So again, let's set up our system, okay? And set up 2 equations. Right? Let me just write down over here, what are we missing? Let's be clear, right? We don't know A, we don't know R. Now again, you can do this different ways, but what I need you to do for me is show me that you know how to set up a system of 2 equations, okay? So here we go. So we have T6, like we said, is 224. We have T17 is 458,752. All right, so our general, this is where we need our general term. This is where people get lost because they try to use the sum formula because they see sum here, right? And I get it where you'd fall for that, right? But we don't want the sum because we need to solve for A and we need to solve for R, so we want to use the general term. So the general term is Tn equals ARn minus 1. So this is from our second lesson from last week, okay? And Tn equals ARn minus 1. So we actually did a question identical to this last week also. The only difference was at the end, instead of saying find the sum, I said I could just change this and say find term 20. That was it. And one little change, right? And all it changes is at the very end. Everything else is identical. All right, so let's substitute in what we know. We know the term is going to be 224, and let's make n 6. We know this term is going to be that number. Let's make the n 17, and away we go. All right, so term, 224 is the term, equals AR to the n minus 1, right? So 6 minus 1, so I'm just going to write 5 right away. Okay, same with this. 458,752 is equal to AR to the 17 minus 1, so it's 16. There's my 2 equations. Now, The second part, normally we do substitution or elimination, right? But in this case, this is the first time we learned it last week, but this is when we can't use substitution or elimination. Do you remember what we have to do? We have to divide the two equations. Now, why do we have to divide? Why can't I just subtract them, right? Well, the problem is the terms that we're solving for, the a and the r, are not being added or subtracted. I'm just going to jump over to that previous lesson. All right, so here we go. This is example 5 from the previous lesson. Remember how, look at, what are the a and d, right? The a and the d terms are being added. The a and the d terms are being added or subtracted. It doesn't matter. The fact is they're separated by addition and subtraction. So we can eliminate using addition and subtraction. That works. But that's not going to work with this case. Here, they're attached by multiplication. So to undo that, we're going to have to divide the two equations, right? You can't subtract it away. We can't take this and subtract that. The a and the r are joined by multiplication. So what I generally do is I put the one with the bigger number on top, just so I can avoid messy numbers here. Generally, the larger exponent I put on top. And 224 on the bottom, AR to the 5 on the bottom. All right, so now when we divide, okay, this side's easy to divide, right? Punch it in your calculator. We go, what's this divided by that? I think I get 2,048. Now, when we divide the other side, the a's are going to cancel. A divided by a is 1, right? We can cancel those factors. And when we divide the r's, remember our exponent laws, we just subtract the exponents. So 16 minus 5 is 11. Cool. Now, how do I solve for r? We're going to take the 11th root of 2,048. So you punch that in your calculator, and we're going to get out 2. All right, so we got r now. R is 2. Now, we just need to solve for a. So now we have one unknown. We only need one equation, right? Two equations for two unknowns. Well, now that we've got one of them taken care of, we just use one of the equations. So let's substitute r equal 2 into, pick one of the equations. I'm just going to pick this one since it's smaller. So I'm going to number these again. Probably should have again to begin with 1 and 2, right? So I'm going to substitute it into 1. There we go. All right, so 2, 2, 4. Let me just get it back to the color there. There we go. 2, 2, 4 equals a times 2 to the power of 5. All right, well, let's do what's 2 to the power of 5. You get 32, right? And then you're going to divide both sides by 32. And what are you going to get? A is 7. Okay, cool. So there you go. Now, up to that point, it's identical to the previous lesson on geometric sequences. Now, after this, the only thing that's different is this. What do they actually want us to find at the end? They want us to find the sum, where before I said find a term, right? Now, if I said find term 20, you would just use your general term equation, which is this guy right here, Tn equals ARn minus 1. They don't want the term, though. They want the sum, so we're going to use our sum formula. Okay? So what's our sum formula? Here we go. Sn equals a times r to the n minus 1 divided by r minus 1. All right, let me just move this up a pinch, and away we go. So sum of the first 20 terms. We said a is 7. R is 2 to the 20 minus 1 divided by 2 minus 1 again. All right, so we're going to punch in our calculator. You know what? I'm just going to save all this time. You can handle this, right? You go 2 to the power of 20. You subtract 1 from it. You're going to multiply it by 7. And then 2 minus 1 is 1, so you're going to divide by 1, which has no impact on it. So punch that all in, and you get 7,340,025. Okay, so that is it for this lesson. Make sure you ask lots of questions if you have them. I'm hearing from some of you, but not a lot from others. So, all right, there you go.